Hey, welcome to the shop. Today we're going to continue to explore laser welding with the XLaserlab X1 Pro and compare several weld joints between MIG or TIG and laser welds. This is going to build on a deep dive that I did into laser welding with this machine about a week and a half ago on the channel, and I'll continue to build on this in one more video where I'm going to build an actual fabrication project using this equipment because I want to see what limitations come up in terms of access, filling gaps, just fitting this equipment into the space that you're working with. Before we get started, I need to touch on safety. This is by far the most dangerous piece of equipment that I have ever used or had in my little shop. It can blind someone from hundreds of feet away, start a fire across the room, or severely burn your skin, even from a reflection that is not straight out of the gun. The PPE is different from regular welding. It's not a standard welding helmet. You need the special one. And there are many other precautions to take. So I encourage you, before you use this type of equipment, to do your research and be responsible. Let's start off by looking at some plain carbon steel and compare it with MIG welding. This is some 1/16 of an inch or 16 gauge carbon steel. I use a lot of this for sheet metal work as well as some tubing, and I usually MIG weld it when I can. I got flux core wire in there. Hold on. All right, here we go for real this time. Now, some people do a whole lot of manipulation and moving the MIG gun around or putting in a bunch of tacks when they weld. I don't do that. I just weld in a straight line. If you got your settings right and a good quality machine, it goes pretty well. You can see that heat following right along here, and I'll get a nice bead. Now, I could probably travel a little bit faster and get a little bit smaller fillet weld, but I'm just reading the puddle and letting it flow in as it does, so it takes a little while to weld a joint this size. So let's take a look at this weld bead right here. You can get something as consistent as you are, but you can see I have a little low spot there, it's a little higher there, because all of the variables like your angle, your stick out, your travel speed are all manually controlled. There's a little bit of spatter there, but not much, and definitely an acceptable result. I mean, this works, but it'd be interesting to compare it directly with the laser weld. Well, I think I just welded right through it to my table. All right, I turned that down a little so I don't weld it to my table again. I forgot to turn on the wire feeder. Third time's a charm, right? The laser weld took a little less than half the amount of time of the MIG weld, and you can see how much faster I'm traveling, and my standoff distance and travel speed are both controlled by that wire. I don't mind this start here where I didn't have the settings quite set up right with the wire feed, but on a run like that, I mean, I can see this for sheet metal work being a no-brainer because you have basically no cleanup there at all. And if you look at that heat tint, that heat input is so much lower. Now, you still do have a little bit of warp and wobble there in the bottom. That's just going to happen. But let's look at it side by side with the MIG weld. MIG weld's not bad, but you tell me which one you'd pick. Now, this is the MIG weld. It's welded on the back side here, and I'm going to bend it open from the root. With that huge weld, I don't expect there to be any structural issue with that at all. All right, no surprises there. The one really in question is, can this little tiny laser weld hold up to that? For all intents and purposes, I'd say that little tiny laser weld that was faster and easier to do is just as structurally sound as the MIG weld. So I'm impressed and a little bit surprised, to be honest with you. Now let's go up in thickness to 1/8 inch thick with MIG and laser. Once again, just a steady, fairly straight progression, not very much weave to it, just a very, very slight manipulation. Now, I'm able to travel a little bit faster this time with the higher settings that I've put the machine to for this thicker material, but it still is fairly slow going along this coupon. Here on this 1/8 inch thick, I got a pretty typical MIG weld right there. There is a little bit of weld spatter here and there that I can clean off pretty easily. And if I fine-tuned my settings, I could get rid of that, but it's something you end up dealing with a little bit when you're MIG welding. Now, even just for getting nice little tacks on things, I mean, those are slick and I can pick it up right after. So pretty handy for that. Let's weld it out. The machine is maxed out on 100% power, and it actually is set with a slower wire speed, which gives a slower travel to help with penetration. So the time savings isn't as pronounced here. It's a savings of about 25% compared to MIG on this thickness. All right, look at that slick little bead. I mean, that was easy as it gets, and it's perfectly consistent because it's basically an automatic process. And last week when I took a cross section of one of these welds on 1/8 inch thick material, I found that the penetration was so good that the strength was surprisingly high for this thickness of material. Now, if we compare that side by side with the MIG weld, you can see how nice that would be with no cleanup in a lot of decorative applications, because aesthetics do matter in a lot of cases. That said, MIG weld still works pretty good. All right, now once again, it's only welded on the front side, not on the back. So we're gonna bend it open from the root. Root's not opening up at all, and I wouldn't expect it to with that big old fillet in there. Good sound weld for a lot of structural applications. Next up, the laser weld. Let's see how this holds up. Just about as good. Now I do have these 2 tacks on there, so you know, those could have some impact on the test, but I don't really think so because they're so short. If it was gonna pop open, it would. Let's go ahead and clamp this tight in the vise just to test it a little more. Again, I think those 2 tacks would have just popped open if the root was going to pop open there. I don't think that's enough to hold it. And this is consistent with what I found last time I tried this for last week's video. Really impressive strength here on this 1/8 inch or 3mm thick material. Now let's move up one more thickness to some 1/4 inch, and I'm going to remove the mill scale before I MIG weld this. Now, in addition to the learning curve on technique, there is a learning curve for settings, and with MIG, even when you have good synergic settings like my machine does, you still have to fine-tune them for different joints and positions, and I'm finding the settings on the laser welder to be much more straightforward and simple. So let's take a look at this MIG weld right here. Now, this process works so well on 1/4 inch thick that I don't see a lot of advantages that you would get from the laser, but since a lot of people have asked, let's just give it a try. Now this time, instead of the grinder, I'm going to use the laser cleaner to remove some of this mill scale. That's pretty cool if you ask me. I don't know that it was faster than the grinder. I'm still going to hit it just so we can have a consistent surface between the 2 different methods. There's a little tack over mill scale. Some people were wondering about welding over mill scale. I think that's what you get. Probably a bad idea, but it seems to work better in some processes. That tack pulled pretty hard. I got to squeeze this down right here. Now I'm traveling even more slowly here, which is going to help to get even better penetration on this thicker plate to do the best that we can, even though this is really pushing past the limits of what this machine was intended for. All right, well, here you go. I did not even know what to expect on 1/4 inch thick plate, but that turned out really good, really slick, but very, very small and probably not adequate for most structural situations. See, if you compare it side by side with the MIG weld here, you can see that I have enough built up here. This is probably a 3/16 inch fillet on 1/4 inch plate. This is going to be less than an 1/8 inch thick, but probably better penetration. In fact, if you want to look up something cool, look up laser hybrid welding. There are some industrial situations where they're running MIG with a laser in front of it to increase penetration. Pretty slick, probably not a good idea for a DIY setup, but I actually think there may be some situations where this would make sense for 1/4 inch, or at least for tacking it up. I mean, it seems to be pretty stout. Let's see if we can't break these 2 open and learn something from that. As always, weld it on one side, bending it open from the root for worst case test. Now, if you aren't familiar with a fillet weld break test, it checks two different things. One is that you consumed the root of the joint or this edge of the plate, and it did all the way across here. Now, there is a straight line here, which usually would indicate that you didn't get into the root of the joint, except this is an automatic process. And if you look, that straight line is significantly below the surface of the plate. So we had good penetration into the root. The other thing that you're looking for is any porosity or discontinuities in here, and we don't have anything like that. So it's a good, sound structural weld that passes a fillet weld break test. That being said, it's a very, very small fillet weld, less than 1/8 of an inch. And that's just too small for pretty much anything structural along 1/4 inch. So a little machine like this with a single wire feed just isn't going to get it done on this thicker structural. And yeah, you could run a bunch of passes and probably get one that was big enough, but that wouldn't make any sense. There's no advantage over running just a MIG weld. Now, with a bigger machine and twin wire feed, you probably could do it, I think. But this one's probably a no-go on 1/4 inch for me, unless it was some kind of decorative thing. Now, if you look at the fillet weld here, it's just much larger. Let's see if we can't break this one open. I don't think I'll be able to do it on the bench here. Not gonna happen. Let's move to the press. There are many things on YouTube that you shouldn't try at home. This is one of them. Pushing pretty hard on that thing. You can see how hard the press had to push to actually break that open, and you had a lot more strength to this weld. But the penetration here is not that good, and that's pretty typical with short circuit MIG. If you look at how much original plate is left here, it's quite a bit less than the short circuit MIG. So the laser actually penetrated better. You just can't get a big enough fillet weld in a single pass with a little machine like this, and you're better off running a MIG weld there, and you're gonna have something quite a bit more sound in that case. And I think as you go thicker, honestly, wire feed processes like spray arc MIG or like dual shield flux core still have a leg up on laser, at least for the time being. But we'll see how the technology and machines evolve over time. When it comes to welding mild steel, for that 1/8 inch or 3mm thick and under, this laser weld has a ton of advantages, particularly when aesthetics are important, because that tiny little weld with no cleanup on a railing or something like that, just gonna be money. Also on sheet metal work, things like that. Now, as you get to thicker materials, the wire feed processes really take over. MIG, and even you get into dual shield flux core and maybe some spray transfer if it's real thick. And I don't see a lot of advantages to using a laser, and a laser of this size just can't deposit enough weld to get the strength that you need. Also, I can envision some practical challenges where you're trying to fit into different areas. And with this gun, you have to drag. It has to be perpendicular to your joint. And it's just kind of large. So I think there are cases where it wouldn't fit in. And when it comes to things like filling in gaps and tying in the start and ends of welds, I'm still learning on this, and I'm not 100% sure how to do it. And so I might gravitate towards MIG in that situation just because I have more experience with it. Now let's compare some TIG welding on stainless steel with some laser welds. So here's some stainless steel, and the two issues you face with stainless steel are one, oxidation, so that discoloration that you can get on the surface affects your properties and also corrosion resistance, and two, you get a lot more distortion or warping because of the thermal conductivity and the thermal expansion of the material. So I want to test those, and the way I'm going to do it is weld a lap joint right here, and I'm not going to tack this side, so it'll pull open, and we can see how much it pulls open with TIG and how much it pulls open with a laser weld. Now, it took me a long time to learn how to run a TIG weld like this, and it's honestly exhausting to do because you don't have very much margin as far as your arc length goes. You've got to keep it short here on the stainless, and you have to keep moving along at a fairly decent rate to keep from overheating your material. So the learning curve here is really, for me, it was pretty difficult. So we have a pretty good light straw color all the way along here, reasonably consistent fillet. If we look at the back, you can see the heat tint because I didn't have any back purge or anything. Okay, I'm gonna go ahead and tack this up in the same way. I'm not gonna use any filler for the tacks. Well, that was definitely a lot faster and easier than the TIG weld. I mean, that took just a few minutes to learn how to do, where running a TIG weld like this, and I'm certainly not the very best at it out there, but this took me a long time to be able to do. Now, there's a little bit darker color here because I didn't have a big 15 cup like I did on the TIG weld, but if you flip it over, it's pretty clear based on the heat tint here that there's a lot less heat input with the laser than there is with the TIG weld. Now, my original intent was to look at how far it pulled open on each of these to be able to tell something about distortion. From what I'm seeing here, they look pretty similar. So I think I was getting just about as much warping from the laser weld as I was from the TIG weld, but I don't know that that's even a good test, and probably something to try to look into a little bit more. Well, let's bend these things open and see how they hold up. Start off with TIG. Pretty good. Real test is how long I'm going to put up with this Harbor Freight wrench. There, we got it. Had to work on that a fair bit to get it to pop. Remember, it was a lap joint, so I'm looking for penetration down into the bottom of the plate here, and I got it all the way along. There was not a lot of throat to it because that weld had a concave shape. But certainly strong enough for a lot of situations. This little thing looks like it's quite a bit smaller, but depending on the penetration, what's called the effective throat, or how much meat there is holding this on, could be a bit bigger. We'll find out. Well, as I'm watching this vise here, I can tell just how well that's holding on. Look at those jaws flexing. I can't believe this one. There's that crunch, that stainless steel crunch. I did not expect that. This laser weld held up a lot better than the TIG weld, to be honest with you, though the TIG weld took a fair beating as well. Now, if you look at the effective throat here, the actual area through the fracture surface, you've got just as much with that laser weld as you have with the TIG weld, just because that penetration is so good. And look how smooth and consistent that is. I mean, that's going to be a really reliable process, especially if you're training a new person. That being said, the TIG weld has a lot of advantages, and you could definitely build this up to be a lot stronger than it was. Now I have a little bit thinner material. This is some 16 gauge. I'm just going to run a bead on plate right across the center with TIG and then with laser, and we can compare the distortion between the two. All right, we'll take this one with a grain of salt because it's not a scientific test by any means. This bead is bigger than that one. I probably could have gone faster. Perhaps I could have run pulse, but also I could have run pulse on here too and gotten an even better result. But I think it is a fair demonstration to see what can happen with stainless steel when you TIG weld it. And some of that could be avoided with a laser. So again, not a scientific test, but I think it does show some promise for the process to avoid distortion in certain cases if you use it right. I have one bonus joint I want to test out. It's a stainless steel outside corner joint on 16 gauge. This is the joint that I'm most excited for with this machine, and I suspect it'll work great, but let's try it out. I'm not going to compare this with TIG. I'm just going to run it with the laser. All of the other welding on this video has been continuous. In this case, I want to try out the pulse feature on the machine. I'm getting a bunch of little tacks there. I think I need to work with the settings. See right there, it was spaced out too much. I slowed down the wire speed and got something really nice. It looks really consistent from the back side. Obviously, there's no back purge in there. All right, now that I got a consistent bead, I've turned up my gas flow rate a little bit to see if I get a little better shielding. Well, that, my friends, is the weld I've wanted to make with this thing since I got it in. And yeah, I think for this type of thing, it's a pretty good fit. Now let's look at some aluminum. I have a couple different thicknesses here. This right here is 1/16 of an inch thick, so fairly thin for aluminum fabrication, and then also some 1/8 inch thick aluminum right here. So I got something along those lines. When I'm doing this more often, it comes out a little more consistent than this, but it's not terrible here. So if you look at that, it bent clear over on itself right here and didn't open up from the root at all. Now, I've had a lot of questions about fumes with this, and if you eliminate them, you can see the fume coming off of this weld right here. And my air quality monitor in my shop tells me that this produces more fume than TIG, but less than MIG. You definitely want to have ventilation and probably a respirator as well in most cases. All right, well, that was way too easy. You can learn to do that in about 5 minutes. It just pushes it along with the wire and the laser melts it. Way, way easier than TIG welding. The look is very different from an aluminum TIG weld, but it's as consistent as can be. And I can think of a lot of situations where it'd be nice to have this. So when it comes to this thinner aluminum sheet metal, I see myself using the laser a lot compared with TIG. You can see the aluminum sheet is bending around here. It's not yielding at the weld in this case, which is awesome. I would say that that little weld on this thickness of aluminum is just as good as the TIG weld. But let's try it out on some thicker material because we're going to run into some limitations, particularly with the wattage of this machine. I'm going to do the same thing with 1/8 inch thick aluminum, so twice as thick here. And we'll see the difference here. Honestly, I think this thickness is so much easier to TIG weld than 1/16. Once again, some nice little tacks without filler. Now, if you were holding something together that was gonna pull on these probably wouldn't hold up, but it's a nice way to be able to assemble simple things like this. So you end up with something that looks kind of like that, not too bad, and you can really build this up about as large or as small as you want with TIG. You can see with that size of a weld on there, and it was penetrating in pretty good. It's holding up really well. Yeah, that'll work. Really, with the softer filler metals that you have on aluminum alloys, you kind of have to build up the size of that fillet weld. Whoa. All of a sudden, I was getting no power out of this thing. Let's dive into this. I'm going to try changing out the protective lens. I believe when the post flow is too low and you're welding aluminum, some of that fume can get up in there and contaminate the lens. All right, now with the new lens, it seems to be working great. Certainly a totally different look than the TIG weld. It's a tiny little fillet weld, so you're not gonna have that same strength that you get with the TIG weld, but it was super fast and easy to do. And I can think of a ton of products, decorative kind of stuff, where a tiny little fillet weld like this would be completely adequate. Let's go ahead and just do a little strength test and see how this holds up. As always, just welded from one side and bent open from the root, kind of worst case conditions. I got a pull pretty good on it, but it did snap open a lot easier than that TIG weld. So I'm noticing a few things here. One, the weld failed right through the center of the throat. So I had a good fusion on the base and on the vertical section. Two, it consumed that sharp edge all the way along this vertical section here. And so I did have penetration down into the root of the joint, which is great news. So this weld was as good as it could be, and given the size, it just doesn't have enough material there to prevent it from failing in the weld and failing the base metal instead. That being said, I had to pull fairly hard on it, and this would be strong enough for a ton of applications, whether it's decorative stuff or you know, if you had it welded on both sides or tubing, it would be pretty strong, but you don't have as much material there as an aluminum TIG weld to really give it the same amount of reinforcement that we had. Now on stainless steel, I was super impressed with how well that lap joint held on. I mean, it was strong. On aluminum, it was great on the 1/16 inch, but once you got above that, this machine just doesn't have enough power to produce a large enough fillet weld. And in the last video, I got a lot of ideas back on things I could do, but at the end of the day, when the power is maxed out and I'm feeding the full wire in, you're kind of out of real options, and sweeping a little more, a little less might make a small difference, but it's not going to make up for the amount of size that you really need on an aluminum fillet like that. So some things to think about there. Now, if you are interested in picking one of these up, I have a discount code listed in the description that you can check out that'll save you a bunch of money when you go to buy one, and it helps the channel out too, so it's kind of a win-win there. And I'm looking forward to putting this to the test on an actual fabrication project in the next video. So be sure to keep an eye out for that, and we'll look at some of the practical limitations of using this process when it comes to actually building a product. Thanks a ton for tuning in. We'll see you next time.